2021 videos from UTM, where I taught an equivalent of star B52. They're available. So Zoom links no longer work, but they were saved, and CMS systems administrator is working on having my UTM videos on the stuff similar to star B52 to be on this course Quercus page to help you review the previous stuff if you forgot it already over the summer. Yeah? So if you remember it well, you don't need to watch it. 4 last videos, they're actually available on YouTube, and there is a link at my profile to these YouTube videos. Okay? Now, I hope you hear me well, and first of all, I'm going to talk about some requirements which we already made available to you. So you have this syllabus already, yeah? So I asked someone to check yesterday that you had access. I know there might be problems when you watch and read on yourselves, yeah, but it's your technical issue. Yeah, so if you have a stationary computer, desktop, yeah, so there shouldn't be a problem, yeah? So anyway, you know where to find me and when. So TA office hours will be announced in the due course. So it wasn't available last year. So it's what? So I need actually, okay, yeah. Okay, so I probably will use, come on in, please. Plenty of space in the very first row. So if you need to move during the lecture, say if you don't see well on chalkboard, it's perfectly fine, yeah? So if it's for your learning, I'm very accommodating, okay? So as I said, there will be lecture notes. Today's lecture notes, they contain 4 exercises for you to work on. However, I do not collect solutions to your exercises. However, I will eventually post solutions for your own benefit, but you need to try doing them first. So it's a theoretical, proof-based course of probability theory with some stochastic processes. So probability theory and stochastic processes actually, this is my area of expertise. I publish in probability and stochastic processes. Okay? Then I should say that when you learn the things in B52, although it's calculus-based, it's not really the hardest thing. The hardest things come in this course, which is proof-based. Okay, and you'll see it even today. And you probably looked at Professor Evans' page for star C62, did you? Yeah, so some did. So Professor Evans, whom I have known for ages, spoke to me about C62. We met for 3 hours. and I have access to his lecture notes from last year, but he did not use a specific textbook. Okay? Because there are so many different topics to be covered that it's not really feasible to use one textbook. I'm going to use 5. It doesn't mean you have to purchase all 5. Yes, so your budget is limited. Okay? So Patrick Billingsley book, it's more like graduate level book. 4th edition is now being shipped from Math Sciences Library in St. George to Scarborough Library, so it will be put on reserve. So 3rd edition, which is very similar, looks like that. Okay? And for 3rd edition, the PDF file is available online. Yes, so you have this link for Colorado EDU. Come on in, please. Pretty, a lot of space here. Okay, so okay, the second book is by Professor Michael Evans and Jeff Rosenthal from St. George's campus. So this is the book. Fortunately, it is available for free at Jeff Rosenthal site. So there is a link, and I will actually use only parts of this book, say chapter 11, and even today I will refer to particular topics in chapter 2. Yes, so I will try to build bridges between B52 and C62 today. By the way, I noticed some of you take photos. It's perfectly okay. So when you take photos of chalkboard, etc., that's great. But please do not forget, send me copies of your photos, okay? I'm asking you to do that because it gives me a better idea of what is seen on chalkboard, and who knows, I might make an error when writing something on chalkboard, and your photos would help me correct them later on. Is this clear? Okay? So perfectly fine. Taking photos, send them to me, please, for your and your peers' benefits. Okay? So anyway, this is a very useful book. However, actually, it's more like B52 and B57 book. Only parts of it are useful for this course. There are challenges here, which might be suitable for C62 students as well. Okay? Then there is a book by my former chair, Professor Boris Gnedenko, who actually signed documents for awarding me PhD degree. So he passed away a long time ago, and wrote an excellent textbook, which is of right level. So he wasn't my formal PhD supervisor, but I wrote one chapter in my PhD dissertation under his direct influence, and we spoke a lot. So one secret on education I learned from him is give the core in detail to make sure students would understand the main things. If something is missed, students should be able to catch up on this later on. So It's an excellent textbook. Professor Gnidenko was one of the pioneers of the extreme value theory for maxima and minima. His contributions to limit theorems of probability theory, quality control, and so on were enormous. And I like this textbook. By the way, it also has a nice chapter on the history of probability theory. If you are interested in it, consult his book. And fortunately, it is available for free from U of T library, so there is a link. Then there are a couple of books by Sheldon Ross. One of them, actually, I brought it with me today. So it's 10th edition of his A First Course in Probability. It is not cheap. Hardcover is not cheap. I'm not asking you to buy it. Scarborough Library will, of course, buy it. But there is a global paperback edition which is available for free. And there is a link. It's on the bottom of the screen now. You click on it, and you get a link to Global International Edition. OK? And then when we move closer to the end of the course and study stochastic processes, we will use my notes as well as some textbooks. There is a book by the same author, Sheldon Ross, Introduction to Probability Models, 12th edition. So it will soon be on reserve at Scarborough Library. But in 2015, 2016, I taught Star 447, Star 206 in St. George. So I used 11th edition of the same book for stochastic processes course in downtown. At that time, I asked math librarian to purchase online access, and the online access to 11th edition is still available through U of T library. Okay, so it's very similar. Is this clear? Yes? So therefore, I certainly am concerned about your budget. I know it's hard to make ends meet when you're students. And I will specify what exactly I will be using for my lectures. Okay? I'm not asking you to read all 5 books. It's simply not possible. Also, I taught advanced probability theory in some other places. One of them was Tokyo Institute of Technology. It was a long time ago. I was a recipient of British Columbia Asia Pacific Scholars Award to teach a course in Japan. So I have my Tokyo notes. I'll make them available if necessary. I cannot put too much stuff on Quercus because there is space limitation of what can be there. But if someone would need them, of course, I'm prepared to share them with you. OK? So is this issue on textbooks clear? OK? So don't be afraid. I'll specify particular chapters. OK? Now, course description, which you are expected to read yourselves. basically, there are 3 major subtopics, but there's going to be some parts of them which I don't want to get into details. We first consider rigorous probability theory that is going to involve some concepts of measure theory. So Billingsley's book, it's doing everything right, but it's hard to read. Gnidenko's introduction is easier to digest, but you're welcome to read both. Then we will discuss numerous limit theorems of probability theory, which is my cup of tea. I have research monograph on limit theorems, and I work on limit theorems of probability theory and stochastic processes. And then, closer to the end, we are going to talk about stochastic processes. So we'll consider some topics of the theory of stochastic processes. The most important of them is, of course, Brownian motion, or the Wiener process, which describes the chaotic movement of molecules in this room. Some of its versions describe stock price movements, but it will be closer to the end of the course. Come on in. Okay? But there will be other topics like Markov chains, martingales, stationary and Gaussian processes. And then more stochastic processes will be considered in STA C63, the follow-up course, which I will teach in the winter. Okay? Now, the marking scheme is going to be similar to what was in place last fall. So your work on the exercises will not be graded. So there will be 2 midterms, and I made requests for the time of the midterm. The first one should take place during the week right after your Thanksgiving break, during which you're expected to catch up. Okay? Then the second one should take place during 10th week. So specific dates will be announced in the due course. Okay? So there will be open books. Cell phones, of course, will not be authorized. Okay? So the internet will not be authorized, but they are going to be open book. Yeah, spoke with Professor Evans on what he did. It doesn't mean that the tests will be simple. Okay, so term tests will be worth 25% each. Final exam will be worth 50%. Okay. Now, I wouldn't be talking much about missed work policy, so you need to read the stuff yourselves. So there are comments on communication policy. On accessibility issues, health and wellness, and academic integrity. So you ought to be familiar with the rules. Okay? Questions? Go ahead.
So there's only 3 evaluations, right? Only term tests and final.
Correct.
Because in the forecast, in the grades,
Yeah, it's going to be modified. Okay? So the syllabus is what explains what is going to be taking place. Clear? So it's the same assessment scheme as was in place last fall. More questions on the syllabus? Yeah?
Just to clarify, the term tests are open note. Is the final also open note?
I will specify. Most likely, yeah. Yeah, okay. So more details on test format will be provided in the due course. Okay, now I want to start with math. Okay, and you all have my email. I try to respond to email messages, sometimes promptly, but not always. Okay, so I don't really respond overnight. Okay? Okay. Now, okay. So, yeah, I need to pull it up. Okay? And I need more light. And I already checked this room. There are blind spots here. If you can help me get my... so off. So that's what I need to do.
Okay, lovely, thank you. Let me pull out your
So it's here, yeah. So I can take it. Yeah.
Just make sure I take it out safely.
Sure. Okay. You're welcome to move closer to chalkboard. Feel free to move during class meetings, okay? I'm very accommodating. Thank you. Thank you.
Is there anything else you need from me, Professor?
Huh?
Anything else you need from me?
I think that's it, but you are going to stay in the
I'll
room,
be
yeah?
here, yeah. But if you need anything else, just
Yeah.
call me. Give me a little wave.
So for now, I think just an important thing is that you record what is written on chalkboard. Yes, so this would be the main concern. Of course, I will post the notes too. Okay? Okay, folks. So this is the topic of today's class meeting. So first of all, going beyond star B52. Probability distributions which are neither discrete not absolutely continuous. The keyword is absolutely here. So can you see it well? Like I know it's a blind spot. Like I cannot write too far up. Am I right? Okay. So what actually happens is in B52, you learned about two major classes of probability distributions. Discrete distributions like binomial, Poisson, geometric, yeah? And continuous distributions like normal, exponential, what else? Chi-squared, you remember it? Or not? Yeah, but there are quite a few. And the world map of probability distributions is not that simple. So, for instance, there are distributions which are neither discrete nor continuous, and they are very important for the theory of probability as well as for applications. Okay? But let me just remind you that what you learned in B52 is that for discrete distributions, we have PMF, little p of x, which is probability that your random variable x takes on the value x. So there are more details in my notes. However, I need to remind it because I'm going to use this terminology in the due course. Yeah? So for absolutely continuous distributions, we have the PDF, or probability density function, which is sometimes denoted by P of x or little f of x, where little f stands for frequency. Yeah? And what else did we have for such distributions? Do you remember the CDF or the cumulative distribution function? So it rings the bell, yeah? Okay. Do you remember a connection between PDF and CDF? Yes. So it's related to the fundamental theorem of calculus, yeah? So the PDF is the first derivative of the CDF. Okay? But in rigorous probability theory, including C62, the distributions which possess the probability density function, they're really called absolutely continuous. Okay? From now on, the distributions which were called continuous in B52 are going to be called absolutely continuous. Why? Because there are continuous distributions with continuous CDF which do not possess the first derivative. That's life. Okay? And we are going to talk about such distributions today. But this is already the first major difference between C62 and B52. Okay. Okay. So let me just remind you that a generic, absolutely continuous random variable capital X is characterized by its PDF, which I denote by a little p of x, and the CDF denoted by capital F of x, such that capital F prime of x equals little p of x. So you know this character, it's not Chinese or Japanese 3. Okay? It's actually the identity sign. So when I taught in Japan and used this character, so teaching math course, so I had to be clear that I was not writing number 3, of course. Okay? So you, of course, know that. So it means that these two things are equal to each other identically, and then we have the fundamental theorem of calculus that capital F of B minus capital F of A for absolutely continuous distributions, which is probability that your random variable x is between A and B, is the integral from A to B of PDF P of x dx. Yes, so you, of course, saw this result in B52. So, and the other thing which I should make clear at the very beginning, but you really will get into such details during our second lecture, that there are random variables which are primary and probability distributions which are secondary. And you should not mix apples with oranges. Okay? So frequently students think about random variables as distributions. So random variables are functions. Okay? But the domain is the sample space. Very good. Yeah. And the range is a subset of the real line. But we'll start such things next week. I promise. Okay? But for now, actually, keep in mind that a random variable, so random variables frequently are abbreviated by RV. So RV stands for a random variable. A random variable can have numerous probability distributions. Is it clear? So do you see everything which is written on chalkboard? Okay, so if something is unclear, so ask me to repeat. Yes, so if you want to take photos, that's fine. So, but you let me know if you want to take pictures. So then I'll use the next chalkboard, and then so random variables are primary. So that would be random variables which are functions. Their domain is the sample space. The range is a subset of the real line. And then the secondary thing is the probability function or the probability measure on your sample space. And for a random variable, it could be the same function for which we are going to have several probability distributions. Okay? There are ways to switch from one probability distribution to the other one. Say in financial math, there are so-called families of Escher transforms. It's one of possible approaches to price stock options, for instance. So if you heard about Black-Scholes formula, so a probabilistic proof of Black-Scholes formula involves switching to a different probability measure. Okay, but we'll talk about it closer to the end when discussing some topics related to the Brownian motion process. Okay? So, okay. It's not for now, okay? It's probably for the exam. Yeah, go ahead.
There's just summer lectures, like
Okay.
all summer lectures.
So you took some summer courses, yeah? Okay. Yeah. I usually ask when I proctor exams, so I ask to leave through the back door and I keep it open. Yeah, so. Okay. Now, I want to say a few words about CDFs. Yeah, so in continuous case, or in absolutely continuous case, CDFs are differentiable. Of course, they're non-increasing functions which increase from 0 at negative infinity to 1 at positive infinity. So occasionally we could hit level 1 at a finite number, and then we'll get stuck at this level 1 for the rest of the real line. Yeah? So they're right continuous, and they have left limits. So capital F of x, or capital F sub capital X of little x, where little x is an argument belonging to R1, and capital X is a random variable under consideration. So by definition, it's probability that your random variable x is less than or equal to little x. Yeah. So in the absolutely continuous case, your CDF is differentiable. So it behaves like that. Yeah. In discrete case, it is like a ladder. Yeah. So it's a stepwise function. And it's also right continuous, which has left limits. Yes, so what actually happens, say x1 is the smallest number, so it's the minimum. Yeah? So your CDF will be 0 up to this value, little x1. So, so what we have is that x is between little x1 and say little xn, although the range can be a countable set, like for geometric distribution. So your CDF will have a left limit, so it can be a dot, like you can have a circle, but I usually have a left arrow, meaning that there is a left limit. And then at this first point, x1, there will be a jump. There will be upward jump. And the magnitude of the jump equals P1, where P1 is probability that x takes on the value little x1. And then it's going to remain at this level till the second value x2. And at point x2, it's going to make the next upward jump of magnitude P2. Okay. And then it's going to be flat till this value x3. And at this point, it's going to make another jump of magnitude P3, etc. Okay? So, and then we have two possibilities. It could creep towards the level 1, never reaching it, which is the case for geometric or Poisson distribution, or it could hit this level 1 at a finite value of the range. Say for binomial distribution, the largest value is n, which is the number of trials or tosses. Yeah? Therefore, it's going to become equal to 1 at the value of x equal to n, and then remain at this level forever, because CDFs can never go downwards. It either remain flat or go up. Clear? Okay. And that's, folks, that's what you were expected to learn in B52, although I realize that CDFs, it's actually this stuff was among the hardest topics. Am I right? Okay, so there are some additional notes on this stuff, which you're also welcome to review. And now I'm going to talk about different things. Okay, let's keep this stuff available for now. So if you like, I'm going to erase the very first stuff. Okay, so, and if you'll need to take photos of the previous chalkboards, let me know. They're still available for now, okay? Okay. Now, there are some topics in B52 book, although last fall you used a different one. But this is the book by Evans and Rosenthal. And there are two subsections in Evans and Rosenthal textbook, which are namely subsections 255 and 256, I believe. I think it's also 256. Or it's actually 254 and 255, actually. They are on mixed distributions, and there are mixture distributions and distributions which are neither discrete nor continuous, so which is an advanced topic. And I'm asking you to read these two subsections. I discussed them in my UTM lectures. Actually, one of you, Mikola, he has my UTM lectures, so if you want to start reviewing them, so contact him. You just show where they are. Yeah, okay. So eventually there will be on Quercus page, and in my UTM lectures I discussed mixed distributions, which are neither discrete nor continuous, but very simple ones. Also, they are in two subsections of Evans and Rosenthal book. The one actually which I want to discuss are the so-called zero modified exponential or ZME distributions. So I consider a very special case where the CDF is as follows. Capital F of x is 0 to the left of 0, and it equals 1/2 plus 1/2 times 1 minus e to negative x over 2 for x greater than or equal to 0. What should we check for a generic CDF? It should be 0 at negative infinity, which is obviously the case. It should approach 1 at positive infinity. It's clearly the case because this negative exponent will die out at positive infinity, and you get 1/2 plus 1/2. It should be right continuous, having left limits. Where can we get a singularity? 0. Do you get it? Because you have one formula to the left and the other formula to the right of 0. Let's draw the graph of this function. Okay. Clearly it is 0, so it's flat to the left of 0. And then how much is it at naught? So I plug in 0 here, so it will be 1 minus 1, which is 0. But it's going to be 1/2, yeah? Therefore, it equals 1/2 at 0. And then it will be 1 minus 1/2 times this negative exponent. And then it will be creeping towards 1 at positive infinity, being continuous to the right of 0. But there is a singularity point. It has a singularity at the origin. Clear? What does this singularity mean? P of x, which is probability that your random variable takes on a particular number x, is capital F of x minus the value of the CDF at x negative, which is the left limit, yeah? So the magnitude of the upward jump at a point is exactly the value of probability to take on this particular value. Understood? Therefore, P of naught is 1/2 minus naught, which is f of naught minus f of naught minus, which is clearly 1/2. We have a jump or positive probability to take on this value 0. And then it will have a density component. it's not going to be exactly the probability density function. We can call it a density component. You have a question?
Yeah, I have a question. So you wrote like 0, negative. I was just like 0 minus. I was just wondering what that means.
So it's the limit. It's calculus stuff. It's the same as in calculus. Yeah, so it's the limit of f of x as x approaches 0 from below. It's Calc 1, yeah? Which you took a long time ago. That's why I'm saying math concepts should circulate all the time, yeah? So it's great to have so many prerequisites, but we forget them, especially after the summer, yeah? Okay. So did I convince you that this distribution is neither discrete nor continuous? Why do we need to consider such distributions at all? It's not to make your life miserable. This is a real life distribution. Do you know that exponential model is commonly used to describe the life expectancy? Yeah, you know that. It's also used in quality control to describe the life length of a particular device, say a light bulb. But did you ever experience the situation when you insert new light bulb, you turn on light and it failed right away? It happens, yeah? It happens with other devices in your car, like you got something brand new for which you paid a fortune, then it failed before the warranty period. Of course, you would get it replaced for free, yeah? But there is always a chance for the equipment to malfunction right away. Or with a lifespan of a human being, there are stillbirths, so which means that life expectancy is 0 with small but still positive probability. And in case of a live birth, the lifespan is going to be exponentially distributed. So technically speaking, it's not exponential, but rather 0 modified exponential distribution that describes the life expectancy. Understood? So this is an important distribution in P&C or property and casualty insurance. Okay. Now, so I need to erase this stuff. So if you want to take a photo, or you had enough time to take a photo, of course. Okay. Now, I consider the general case of ZME model. So here I have 2 parameters. Which are rho, RHO. So you know this number, okay? Or actually, it's the letter rho. So it takes on the values on unit interval where 0 is not, but 1 is included, and a real parameter m greater than 0. So, and capital F sub rho m of x is defined as 0 to the left of 0, and 1 minus rho plus rho times 1 minus e to negative x over m for x greater than 0. So what was considered before corresponds to rho equal to 1/2 and m equal to 2. Yes, so I just considered the special case. So here, when x is 0, f of naught is 1 minus rho. Yeah, so probability that the corresponding random variable x sub rho m takes on the value 0 can be shown to be equal to 1 minus rho. And if rho is 1, you get the exponential distribution considered in B52. Clear? So it's the same idea. Therefore, you will have the upward jump equal to 1 minus rho at 0. Otherwise, it's going to be continuous CDF. So the derivative to the left of 0 is 0. The derivative to the right of 0 is going to be the exponential function. Yeah? Yeah? Well, I should write x greater than or equal to 0. Thank you, yeah. So that's what you meant, yeah? Yeah. Thank you. Okay. And what I want to present now is the first exercise for you to think about. You'll have these exercises neatly written, and my lecture notes, they're going to be posted reasonably soon, but not today. So, exercise 1 is try to find expectation of such random variable and the variance of this mixed random variable. And the hint is use formula 253 on page 68 from Evans and Rosenthal textbook. Yeah? So you need to represent f of x as certain coefficient alpha times fd of 0 of x plus alpha 2 times f a c of x. So you need to decompose your CDF, which I just presented, as a convex combination of discrete and absolutely continuous cumulative distribution functions. One of them actually will be the CDF of point mass at 0. The other one is going to be exponential distribution. This is a hint. Okay? So alpha 1 and alpha 2 are between 0 and 1, and alpha 1 plus alpha 2 should be equal to 1. So when you have such a decomposition, so we call it a convex combination. Okay? So, and then you basically would need to find expectation of discrete and absolutely continuous paths separately, and expectation of this distribution is going to be the corresponding convex combination of expectations of discrete and absolutely continuous paths. Does it ring the bell? Okay? But you need to read some stuff from Evans and Rosenthal, or perhaps contact Mikola, get my 256 videos from him, which he already has, okay? Yeah, so I just spoke with the departmental support specialist to start this process of uploading them. It's going to take some time, yeah? Okay. So, but you don't need to solve all these exercises right away, yeah? But you might want to start reading the corresponding more advanced subsections from Evans and Rosenthal book, okay? So, also, this is an interesting distribution. I studied it, and I actually published a paper in a Dutch journal with a Latin name 15 years ago. So it has more detail on ZME. So it's titled on structural and asymptotic properties of some classes of distributions. So it's more advanced stuff than what you need, but in case you are interested in this class of distributions, I have a paper which I could send you. Of course, it's available online. So it's AAM for Acta Applicandae Mathematicae, volume 97, pages 335 to 351. So it's not necessary to read this paper, but in case you want more detail, so this is a potential source of information. And I now want to talk about continuous but not absolutely continuous distributions. Real fun starts now, during the last 30 minutes of our first lecture. Because I'm going to talk about the distribution which was also dubbed the devil's staircase. That's how it is known in probability theory. I'm serious. If you Google the devil's staircase probability theory, you are going to be referred to counter distribution. So,
Is there any reason why it's called double staircase?
yes. I'll tell you later.
Okay.
Okay? Don't worry. There are singular distributions. Which are neither discrete nor, or actually no, which are continuous but not absolutely continuous, which means that CDF is a continuous function, but there is no PDF. Okay? Therefore, the fundamental theorem of calculus is not applicable. Go ahead. So singular distributions which are continuous but not absolutely continuous. Did you get it? Okay. So therefore, CDF is a continuous function. There is no PDF. Hence, you cannot differentiate your continuous CDF. You, of course, when you studied calculus, I know you even took calculus of several variables. Have you ever thought about real-life examples of continuous but nowhere differentiable functions? So in calculus, you might have heard about an example constructed by 19th century German mathematician. Huh? Which one? Weierstrass. So Weierstrass. Yes. So you heard this name, Karl Weierstrass. So it's S-umlaut, you in English you spell it as double S. So he constructed such an example, which was artificial back in 19th century. Around in 1920s, German applied mathematician and philosopher Norbert Wiener, whose work we will study closer to the end of this course. He realized that the typical trajectories of the Brownian motion are continuous but nowhere differentiable because they describe the chaotic movements of molecules. Molecules hit each other and then they go in different directions, and it happens all the time. So they are nowhere differentiable because they hit each other all the time. So there are such functions. There are functions which are continuous but nowhere differentiable. And but for Cantor distribution, it is differentiable somewhere but not everywhere, okay? But closer to the end of the course, we will study trajectories of the Brownian motion, also known as Wiener process. So Norbert Wiener was my hero during my graduate studies. He not only made essential contributions to the studies of mathematical properties of the Brownian motion, he is considered to be the father of cybernetics, and he really was a thinker. Okay, so remember this name. So he provided real-life examples of continuous but nowhere differentiable functions. But now let's talk about one such example of singular distribution known as Cantor distribution. So the first name was Georg, which is German version for George, of course, yeah? So it's discussed in my notes. There is also a discussion in Billingsley's textbook. Or you can find it on the web and also in Ross' first course book. So the first thing I want to discuss is the so-called Cantor set. And so it's also the devil's staircase. Okay, so Cantor set is a subset of the unit interval. So what you actually need to do is you split your unit interval into 3 parts, from 0 to 1/3, from 1/3 to 2/3, and from 2/3 to 1. And then you erase the middle interval. You may do it, yeah? So let me erase it. Then I have 2 remaining subintervals of length 1/3 each. And I do the same thing with each of these 2 remaining intervals. So there will be a middle interval here from 1/9 to 2/9, which I'm going to remove. Here there will be an interval from 7, so it's 2, yeah? 7/9 to 8/9, and then I remove this 2 middle intervals. I may do it. So I like erasing, yeah? Then I keep doing it with 4 remaining intervals. And I'll do it forever. Sounds exciting. What will remain? Something. Yeah. Something will remain. We, of course, are not going to get into details now. What will remain? We'll discuss such things later on, but I just want you to get a feeling of what interesting topics we are going to consider in C62. It's a kind of prelude lecture to this course. Yeah? So it's actually going to be a continuum set which is interesting in its own right, but it's also related to counter distribution. So now I cannot move this up. And then I'm going to construct first the counter function. There are numerous ways to construct the counter function. And I will discuss a recursive approach to construct counter function on the unit interval. So f naught of x is set to be equal to x identically. And then for each integer n greater than or equal to 0, the next function f sub n plus 1 of x is expressed in terms of fn of x by the following formula. It's 1/2 times f sub n of 3x for x between 0 and 1/3. It is 1/2 for x between 1/3 and 2/3. And finally, it is 1/2 plus 1/2 times f sub n of 3x minus 2 for x between 2/3 and 1. Yes, so I'll move it up. So it will be available for some time, yeah? So I may consider such a sequence of functions on the unit interval, yeah?
Are they all closed brackets or just some of them be open?
So this closed intervals, but they're going to be continuous. Okay? You work on the sequence of functions, and it is possible to prove using Calc 1 that the sequence of functions on the unit interval is going to converge uniformly to a certain continuous function. With some effort, of course. If you want to refresh your calculus skills, you are welcome to do it. But for now, take it for granted, please. So it's a calc theorem. F n of x, so it converges uniformly to a certain function f of x, where x belongs to the closed unit interval and n approaches infinity. And this is called the counter function, which is on unit interval 0, 1. How it looks like. And now, you'll see why it's called the devil's staircase in a moment. Okay, this is your unit interval. So for now, counter function is from set theorem. Okay? So it's going to be like that. And if you go to counter function Wikipedia, you'll see a nice cartoon about this function. Okay? So it is 1/2 between 1/3 and 2/3. So it's flat here. So it's going to be 1/4 between 1/9 and 2/9. So it will hit level 1 at 1. So here it will be 3/4 between 7/9 and 8/9. And then, of course, it will be something else. But it will be continuous. And it's going to be flat at counter set. I'm sorry. It will be flat at the complement to counter set which we throw out. And it will be increasing on counter set, which has the cardinality continuum. Okay? I don't prove it. Yeah, if you go on counter function Wikipedia page, you'll see this neat graph. So it looks like a ladder, which you don't want to try using. Okay? And this is the most famous singular distribution. In order to make it the CDF, you just need to set it up equal to 0 to the left of 0 and 1 to the right of 1. And then it becomes CDF of counter distribution. Which is continuous, but not absolutely continuous. Okay. So in Ross textbook, there is exercise 713. So this is Ross book, whose global version is available online. So if you have ID random variables xn, where xn is 0 with probability 1/2 and 2 with probability 1/2 as well, then such an infinite series over n from 1 to infinity of xn to 3 to the power n converges to counter random variable as n goes to infinity. And these are basically, so when it's 0 and 2 with probabilities 1/2 each, it's just double the Bernoulli trial. But you need to scale them, but here you deal with an infinite series of random variables. That's not what was studied in B52. It's going to be one of the topics in the middle of the course where we are going to study limit theorems of probability theory, which go beyond the central limit theorem. Okay? So we will touch convergence of infinite series of random variables. Have you thought about such a series over n from 1 to infinity of bn, so let it be I, yeah? Bi of 1/2 divided by n. So bi is 1 with probability 1/2 and -1 with probability 1/2. It's like a Bernoulli trial. So if you consider calc series -1 to the power n over n, so such a series conditionally converges, but absolutely diverges. Yeah? It's second calculus, calc 2. But what if instead of -1, we use Bernoulli trials, symmetric Bernoulli trials, when it's 1 with probability 1, and -1 also with, I'm sorry, it's 1 with probability 1/2 and -1 with probability 1/2. So it's 50-50. What is going to happen? Will it converge or not? Who knows? You'll learn it later. And the last topic is Lebesgue decomposition theorem. It's without proof, we'll talk more about this stuff. So it states that every CDF can be decomposed into the following linear combination. So capital F of x is alpha 1 times f discrete of x plus alpha 2 times f absolutely continuous of x plus alpha 3 times f singular of x, where alpha 1, 2, 3 are non-negative, and their sum is 1. So you can decompose any cumulative distribution function into the sum of 3 weighted CDFs. And sum of alphas can be equal to 0. Say, if you want to get discrete distributions, alpha 2 and alpha 3 must be 0. Understood? If you want to get distributions with PDF, you need to kill alpha 1 and alpha 3. For singular, I noticed you had, for singular distribution, alpha 1 and alpha 2 would be 0. What about 0 modified exponential? No singular part, but alpha 1 and alpha 2 would be positive. Understood? It's a result from analysis which happened to fit the needs of advanced probability theory very well. Henri Lebesgue was a famous French analyst. Okay? And I thank you for your attention. Keep in mind that this is just a prelude. So it's a lecture that gives you an idea what advanced probability theory deals with. But it also introduced some topics which you will learn later on. And there will be additional exercises in my lecture notes. Thank you. Oh, I cannot talk now, sorry. Oh, Mikola, why don't you, so here's